I'm going to talk about LIGO and how we are trying to incorporate more advanced and modern controls techniques into our operation and optimization of our precision interferometer. I'm an experimental physicist, but and I do quantum optics, but we need a ton of engineering disciplines, very much including controls, in order to maintain and operate and optimize for precision experiments like LIGO. So here's some of the things that we've tried, me and a student, Ian McMillan, to incorporate H2 optimal control with an H infinity bound with LIGO. And here's just some photos of LIGO. We use these quadruple suspensions, hanging wedding cake size mirrors in order to make an incredibly precision device. Here's sort of what some of the chambers look like. It's all these hanging optomechanics with suspensions on top of seismic isolation. And here's what I'll get to at the end, which is an RMS Pareto front. So just as a quick roadmap, I'll give you a little introduction to LIGO, gravitational waves, their signals and control to motivate our problem, give our case study in angular noise and removing what is a kind of bilinear noise coupling, and some of the very tricky aspects of modernizing to optimal control as we've done that, particularly in our very idiosyncratic plant of a gravitational wave interferometer, and then show you kind of what this looks like and what it took to do it. So LIGO are two observatories, both in the United States. Each one is a laser interferometer, a Michelson interferometer with 4-kilometer arms. So you can see here, one in Washington and one in Louisiana. And the principle of their operation is, as Michelson interferometers, they take a laser, they split the light, and they measure the differential, like the difference in the distance that the light has taken going down both arms. And what they measure is gravitational waves, which stretch and squeeze. They extend one arm and they shrink the other arm, and that alternates at an AC frequency, an acoustic frequency of, kind of 100 hertz due to passing gravitational waves. Those are formed by binary black holes and binary neutron stars that are inspiraling, they're orbiting, emitting gravitational waves. That expends energy, their orbit decays, and so their waveform actually creates this chirp, and that's what we're looking for in the instrument. And so we've made a lot of measurements now. We have kind of a catalog. Here's what many of them look like. Most of these are binary black holes, and you can see them kind of peak up. These are time frequency plots, where you can sort of see the signatures of this in our background, interferometer. And I'm showing you this both because it's kind of interesting for the science aspect, but also it tells us a lot, like what we need to optimize for is sensing signals against noise. So really L2 is incredibly important for us. Or H2 is incredibly important to us as a metric. And what we're doing with these signals is, once you measure them, you can do all kinds of astrophysics, like test general relativity and get the physics of extreme matter, very dense nuclear matter. So the instrument is optimized, and basically, to get to the quantum noise or the shot noise of a laser interferometer, it requires many, many things in order to isolate all of the environmental noise. So we have seismic isolation stages. They use the world's best seismometers. They control an inertial platform, or they make a platform inertial to the seismometers using feedback control. Then we use a quadruple pendulum to reduce with 1/f⁸ from there. And the seismometers will get us down to something like 10 to the minus 11 meters per root hertz. The quadruple pendulum will take us down to what is around 10 to the minus 20 meters per root hertz in the bucket. And then the noise that we're dominated by is actually quantum noise and radiation pressure in the interferometer. And this coating thermal noise, these are physical processes. One way that we reduce thermal noise is actually using glass fibers for the last stage, so that the Brownian motion of the suspension does not reduce the sensitivity. But notable, this is like a model of the various noise processes that limit LIGO sensitivity and inject noise. Notably absent from here is control systems noise. And that's what I'll talk about, is that's a challenge to actually model, predict, and reduce it in our systems. So one of the key things is this figure of merit. I showed these spectral densities. We're looking for signals, which I showed in the time domain. In the frequency domain, they have kind of this characteristic shape, and then they roll off, that has some maximum frequency and some slope. And we can plug that into a formula to get kind of the signal to noise, how well, like how many standard deviations can you measure that signal? And that's proportional to kind of an observing range in terms of how far away you can see these signals. And just as a figure of merit, for most of for like binary neutron stars, we can see 160 megaparsecs. And that's something like 400 million light years away. So you cube that and you get a volume. So we're seeing like vast expanses of space to see such rare, crazy objects. But this figure of merit is actually really informative to use for control. So a couple of things to see is that the slope at these low frequencies is like at least 1 over f to the 8. And then this overall noise that we kind of have to hit is 10 to the minus 20 meters per hertz. So now if you look at a really technical noise budget where LIGO scientists have actually measured all of the processes, what we're really limited by, particularly at these lowest frequencies, is auxiliary controls, like auxiliary degrees of freedom that leak in through bilinear processes and put a background noise on our system. And this is linked control in other degrees of freedom than our principal one, and alignment control, which I'm going to be talking about, which is very much limiting at these low frequencies. So we reduce these and we get them even as good as this using a lot of loop shaping. And the question is, how well can we do? We have to actually do something optimal. These auxiliary degrees of freedom, the actual interferometer isn't just a Michelson. We use all these resonant cavities. And so each of these is a hanging mirror. So we form many resonant systems, cavities. The system overall is incredibly nonlinear, but then through feedback control, we can make it locally incredibly linear and precise. But each of these cavities has 3 degrees of freedom, and each of the mirrors is on a suspension with 18 to 24 degrees of freedom. So we actually use a giant hierarchical and distributed control system to do this, which actually looks very much like the one we just saw, uses epochs as a stack, CPU control with all of the state, and cascaded biquad sections in order to do most of what we do. And we just use classical controls for all of the design. So what does alignment control look like? Well, alignment control is when you have an optical cavity, the center point of the mirrors forms a beam axis. There's kind of a hard and soft mode for if you're moving differentially or in common mode. This can actually change the radiation pressure dynamics and the spring constants of the suspensions due to the actual light itself. So there's a physics aspect to this along with just the controls design. And it's actually quite a challenging thing to get them both right. And so we just, hack it together with classical controls, and we do well enough to just operate the interferometer, and we iteratively tune it up. And that's been our strategy. So our main method is we diagonalize. We have with pitch and yaw, an X and Y, so a common and a differential, and then hard and soft loops. We have 8 different control loops in alignment that we have to tune up and get somehow optimal so that they don't leak in this noise. And we're only doing so good of a job. So what does the noise look like? Well, when our main channel has 10 to the minus 20 meters per root hertz, it's a bilinear process where if the beam is moving on the center of the optic, if it's off center and you tilt it, it will actually couple directly to length. So if we're getting sort of a 1 millimeter RMS over that 4 kilometers through control, then we can only have 10 to the minus 17 meters of control noise injection, or we're ruining our main figure of merit. And the actual sensing noise of our alignment system is 10 to the minus 15 radians per root hertz, which means that by our signal band, we have to be well above the UGF, and we have to be rolling off quite dramatically. So, and the noise that's injected into the loop that we're trying to suppress is, quite large compared to its sensing noise. So we're dropping 7 orders of magnitude. It's going as 1 over f to the 6, at least in this process where we have the UGF crossover. And we can do this design classically, but how do you get an optimal controller to do this and not make something wild that is not implementable? And that's been the challenge. So this is basically our design, our plant, which is 1 over f to the 4, already a problem for using optimal control. And then we have our measurement noise process and an environment noise process that we do sys-ID on these power spectra. And this is a basic model for how you would try to do this, okay, to design a controller using LQG, say. So this is a hand-tuned design where we have, at low frequencies, we want as much gain as we can. This isn't actually all that much, just because we need plenty of phase by the time we hit our UGF. There's some ups and downs due to the mismatch with our plant design or our plant model versus the design, because it's difficult to keep these to track. And then we have to have it just roll off extremely fast, which is really costly in phase at high frequencies so that we don't inject the noise. And we're doing this all by hand iteratively. And we just don't know, like, when can we stop or how much better can we do? And that's why optimal controls is incredibly important. So, one reason we haven't done it or haven't made good progress is various kinds of inertia. Our tooling is just very good. We use an ID or a shaping tool that we developed that's very similar to the Shape It thing that was just mentioned as part of LIGO's tooling. When you're moving to optimal control, you have to have, like, the weights don't seem like they are objective, although we have a canonical figure of merit, the SNR, we should use it. It's complicated. This is true, but we can move all that complication into software and then use automated sysid. So I think in time, we should actually get past the it's complicated part. And then what we did with this is, H2 indeed makes marginally stable loops, but you can add a simple and rather universal H infinity bound to fix it kind of outright. H infinity, if you want to use that doesn't optimize for noise. So it's actually not useful a priori. You should only use it as a bound for our problems. And of course, people are using AI controllers, but there's always a question of what they're doing to our noise. Like, are they going to inject weird signals and obfuscate our actual astrophysics goal? And how do you even benchmark them unless you have optimal control? So what are we doing here? First off, we have to get kind of an objective measure, like in a canonical figure of merit. So we use the SNR, which is linear with the observing range. If you linearize it against the injected noise, you can get this term, which is just putting an additional additive term in the denominator, linearizing as a Taylor expansion. And then you can make a filter, which is most of this integrand. It's at least the square of the filter is most of this integrand, and you can fit that out. And that is this filter. The challenge, of course, is that it's spanning 18 orders of magnitude here, actually 19. And this is actually in state space rendered, and that's why you're seeing some numerical noise. It took a long time to develop because we're working out of Python, something where we could get this with a really high order filter with such steep roll up. It makes incredibly non-normal state spaces, and this has been a fundamental challenge to us. To actually put it into the model, we keep our flat RMS, which is just the actual noise in the plant. We add this as a high frequency, like an alternate figure of merit. And we actually have to pick off at an alternate point than is typical with stochastic noise problems, because the noise is coupling only through the actuator. Like, only when the actuation applies do you get this bilinear coupling. And so it has to go in this funny other place. And it's easy enough to prove. We probably weren't the first ones to do it, but if you change the relative scaling of these two, you can develop a Pareto front for weighting between these two figures of merit, the overall RMS and the high frequency signal to noise impact of the control. And you can actually go back and forth between the equivalent noise background, like SHH term, and the figure of merit filter that's depicted here. So that's one of the fundamental issues. We then had to do some adjustment to fix up the plant. We need an inner and outer factorization of the plant to make it net equal poles and zeros. We have to split it for the actual actuator noise, and then a lot of really careful numerical work in order to get this thing to solve, even in H2, but definitely with H infinity. And Brownian order reduction is also extremely helpful, but it needs really careful balancing for us to maintain such high order filters with so much dynamic range in them. And what we get is, if we plug this into H2, you can scroll the Pareto front and you can see that you can actually do much better than this hand-tuned filter at Hanford by orders of magnitude, but of course the phase margin goes to 0. But you can improve by a couple of orders of magnitude, actually, in the range lost from the added noise, that's proportional to signal noise, and the total RMS motion in radian. So you can get, sub-nano radian here, which is great. Like, this is already quite a triumph. And you can see that it's designing sort of similarly to the hand-tuned, but it's actually doing better at these high frequencies while doing better at the low frequencies. That's great, except for this phase margin issue. And you can see this with the gain peaking in the closed loop, that you have to crush this down in order to get some robust signal. So what you can do is you can add in this extra piece, and we use the Bernstein-Haddad formulas. They used a necessary-based proof, Lagrangian multipliers, to show how to incorporate an H infinity bound in the 80s. And we can use that. We use an algebraic deflating subspace solver with iterative convergence, and we can successfully solve this thing. We can't yet get convex optimizers to work on this problem, but we haven't tried all the balancing tricks that we've learned in the meantime. And then if you do this, you can now add the H-infinity constraint on the gain peaking itself, which now lets you squash it down. It makes this incredibly rectangular phase bubble, which is neat and not something that humans typically design. And now we can make a Pareto front for the noise that is actually parameterized by the phase margin of this system. And you can just choose one of these and it should be a better filter. And you can see that it's much better than the hand-tuned design. So in summary, what we've done with these results or managed to pull this together is actually just taking our typical design, iterative design procedure and completely transform it into an H2 or LQG controller solve with an H-infinity bound to ensure robustness the same way that we would be doing using classical controls by mandating a phase margin. And now we can just choose where we want on this Pareto front for the exact noise terms that matter to us, our signal to noise versus the low frequency RMS. It took a long time to generate reliable numerical code, particularly in Python, to do this. And we actually haven't successfully used MATLAB's codes for this because you need a lot of additional balancing. But we've now demonstrated it, and we're hoping we can actually put it into the interferometer and then start moving on towards actual MIMO control problems, because our current limit is that the SysID and the modeling for our fully MIMO system and properly diagonalizing it is really the next thing we need to do. And so that's kind of future work from here. And we need to move on some of the technical aspects. And I do think that Julia has a really lot new implementations that will be really important for doing this, moving off of SLICOT. So thank you.
Thank you, Professor McCuller. We're collecting questions from the audience. Are there any questions? Oh. Could you explain a little bit more in detail this technique of the input signal that you use for the H-infinity metric?
Right. Yeah. So I'm surprised that this isn't more widespread, but basically, if you take this Z infinity here called U infinity, and you put it in here, you see that it's actually going around and it's just kind of measuring KP or KP prime here, but that's just the open loop gain. And as of Y measurement, this is just measuring G over 1 minus G from Z infinity to Y measurement, or actually Z infinity to Y FOM 1 is measuring G over 1 minus G, which means that this is an H infinity bound specifically on the sensitivity function, on the closed loop gain sensitivity function, which means that, it really shouldn't go below 1, but if you make it like 1.5, you are insured to get 30 degrees of phase margin. Or sorry, if you make it 2, I'm getting the factors wrong. It's something like 30 degrees phase margin. And so you can just ensure a phase margin by mandating limited gain peaking.
Okay, thank you.
I will mention a caveat that when you're using 2 figures of merit like this, it's not exactly measuring that G over 1 minus G because of the factor from the second FOM. But for us, it's not. It's actually a useful feature. Yeah.
And are you using this kind of technique for many kinds of systems, or you're only in this?
Right now we've just tried it on our alignment system because it was well suited for it and kind of needed to improve the interferometer. But I do hope to try it on some of our other auxiliary degrees of freedom, kind of because we have all this hierarchical control between seismic, suspensions, and interferometer. In some sense, the figures of merit are flowing down from the interferometer into the suspensions, which then flows into the seismic, whereas the noise is coming up from the seismic to the suspension to the interferometer. So I do think that there's a way, if you were to do this simultaneously across all the systems, that may be possible, flowing the figures of merit down and the noise projections up, so that kind of the suspensions and the seismic are optimized for what the interferometer need, and their weightings are coming from the interferometer based off of what it needs. But that's a much, much larger problem that requires a tremendous amount of modeling and bookkeeping. So it'll be some time before we get to that step.
Great. Thank you. Siddisha.
Thank you so much for an very interesting talk. I saw on your last slide, you mentioned about the diagonalizing.
Yes.
So can you comment more on that? Is that when you say you are not, the plant is as diagonal as you think it is it coming out to be a block diagonal, or it's...
Yeah, so this just kind of happens to come out of a lot of the physics of interferometers, that if you work out the actuator, the way that torque causes beam motion when you have the optics and the radiation pressure. So if you didn't have any coupling, like if the interferometer had no radiation pressure, then everything is just kind of diagonal and just adds in sum to like the overall motion of the interferometer, but it's all intercoupled due to radiation pressure. And it just so happens that if you work through that out, there's a basis where it is fully diagonal. And that's just a convenient thing, except that it's inexact, and it makes us have to have like perfect matrices, like output, actuator, and input sensing decoupling matrices. And that's just not true. We do not have perfect decoupling matrices. But if you assume that, it actually is otherwise perfectly diagonal, like as a plant.